Pressure. When dealing with liquid and gases, we ordinarily speak of pressure. For solid, we speak stresses. Pressure, and for solids, we say stresses. The pressure in a fluid at rest at a given point is the same in all directions. The pressure in a fluid, liquid or gas, at rest at a given point is the same in all directions. And we define pressure as the normal component of force per unit area. Pressure as the normal component of force per unit area. More specifically, if delta A is a small area, delta A prime is the smallest area over which can consider the fluid a continuum as previous section for the specific volume, and delta Fn, let me write delta A small area, delta A prime smallest area in a continuum, and delta Fn is the component of force normal to the delta A, and we have pressure P equals to the pressure, where the lower limit corresponds to size as mentioned for the specific volume shown also in the picture as this shape. For example, delta Fn on delta A we have fluctuation for system and delta A prime, delta A. Delta A prime is the place that the continuum is governed. The pressure P at a point in the flowing in equilibrium is the same in all directions. In a viscous fluid in motion, the variation in the state of stress with the variation becomes an important consideration. The considerations are beyond the scope of this book, and we will consider pressure only in terms of a fluid in a equilibrium. The unit for pressure in the international system is the force of 1 Newton acting on a square meter area. In the SI unit, we have 1 pressure, 1 Pascal for the unit of pressure, which is the 1 Newton on a 1 meter square. Two other units are 1 bar, which is approximately 10 power 5 Pascal, or 1/10 megapascal. And also we have 1 atmosphere, Pascal, and equals to the British pound force on each square, which is slightly larger than the bar. In this book, we will normally use the SI unit, the Pascal, and especially the multiple of kilopascal and megapascal. The bar will be utilized often in the example and problems, but the atmosphere will not be used in this book except in specific certain reference points. Consider a gas in a cylinder here. A gas contained in a cylinder fitted with a movable piston as shown in this picture. The pressure exerted by the gas on all of the bodies. Boundaries is the same, assuming that the gas is in an equilibrium state. This pressure arrows shows the pressure on the boundaries in the cylinder, and we have the equilibrium state. This pressure is fixed by the external force acting on the piston, since there must be a balance of force for the piston to remain stationary. Thus, the product of the pressure and the movable piston area must be equal to the external force. If the external force is not changed in either direction, the gas pressure inside must accurately adjust. We appropriate movement of the piston with the appropriate move of the piston to establish a force balance outside the body, which tends to increase the gas pressure. The piston will move instead such that the pressure remains equal to whatever value is required by the external force. In most thermodynamics investigations, we are concerned with the absolute pressure. Mass pressure and vacuum gauges. However, read the difference between the absolute pressure and the atmospheric pressure exerted at the gauge. Atmosphere pressure so the P gauge equals to the P absolute minus the pressure of atmosphere, which will be atm. And in the short sub notes we have this relation for the gauge pressure, and maybe sometimes with P0. This is where the pressure gauge is shown also in this picture. It is shown graphically in this picture that we have 2P pressure absolute, which have the ordinary pressure gauge, the difference between the atmosphere pressure. The following example illustrates the principles. Pressure below atmosphere and slightly above atmospheric and pressure differences, for example, across an orifice in a pipe, are frequently measured with a manometer, which contains water, mercury, alcohol, or other fluids. Let me write the pressure so this pressure difference are frequently measured by a manometer which contains water, mercury, alcohol, oil or other fluid. Consider the column of fluid of was shown in this picture of the height of H standing above point B as shown in this pressure measurement device. Consider the column of fluid of H standing above point B in the manometer the force acting downward at the bottom of the column is we have a force here and also the force from the column of the water for example mg here. So the force is P0 multiplied to A plus mg, which is equal P atmosphere is P0 rho AGH. AH is the volume, where m is the mass of the fluid column. A is its cross-sectional area and rho is its density. Thus, the force must be balanced by the upward force of the bottom of the column, which is P for example here, PB equals to F. This force should be equals to, for example, the PB at pressure B. We have also a pressure A. Because the PB equals to PA, we have the force, for example, here is PBA or PAA equals to, should be equals to P0A plus rho AGH. With eliminating the area of the pipe, we have this relation for the pressure of the point B. Gauge pressure of the point B, the manometer will give us, since point A and B are the same elevation in this column of the same pump fluid, this day pressure must be equals. As we said, overall we have PA equals to P, pressure of fluid, PA equals to PB equals to the pressure of fluid, equals to P0 plus rho GH, or the difference is rho GH, the gauge pressure of this tank, for example. For distinguishing between absolute and gauge pressure in this book, the term Pascal will as well refer to absolute pressure. The term Pascal is equals to refer to absolute any gauge pressure will be indicated as such. Consider also a barometer used to measure atmospheric pressure as this picture. The barometer is used to measure atmospheric pressure. As shown in this picture, since there is a near vacuum in the closed tube above the vertical column of air fluid, usually mercury, the height of the fluid column gives the atmospheric pressure directly from the equation P atmosphere. Because we have the vacuum space here. The P atmosphere is the equals to direction rho GH0. Is the liquid density. Pressure gauge and the atmospheric pressure was discussed how to gauge measure the gauge pressure and absolute atmosphere pressure with manometer and barometer respectively. The next section is the equality of temperature in the next section.